lacan summarily be. It is with a very special emotion that here I speak at the University of Gottfried Wilhelm Leibniz, because in fact it was Leibniz who suggested to Peter the Great to found the Russian Academy of Sciences, of which we celebrate the 300th anniversary today. So several speakers mentioned that they don't speak on ergodic theory, so this talk is in fact on ergodic theory, and in fact on ergodic theory in infinite dimension, and let me start by a specific example. So I will consider a power series, a random power series, so where the coefficients are independent Gaussians, and independent complex Gaussians. So independent complex Gaussians. And so I consider the zero set of this random series. So the radius of convergence of this random series is 1. Just choose your favorite criterion for computing the radius of convergence and apply it. So it is 1. And so I consider the zero set. This is a random subset of the unit disk, because the radius of convergence is 1. But in fact, it is useful to consider this unit disk as the Lobachevsky plane, and for the following reason, that in fact this zero set is preserved by Lobachevskian isometries. This is not completely obvious. In fact, the Gaussian function itself is not. So it is not only not completely obvious, but in fact, this is checked by a computation. It's a very beautiful, explicit theorem by Peres-Virag, which I will precisely formulate very shortly. But just for me, the key point is that there is, on this infinite dimensional space of subsets of the unit disk, these are subsets that only accumulate on the boundary, of course. They are roughly unit density. Well, we shall see why. We shall see, again, this Peres-Virag tell us, and I will formulate precisely in a moment. And so this is a random set on which Lobachevskian isometries act. And this will be key circumstance for us. In fact, so this function, the function that is written on the board, is not square integrable. It can be checked quite directly that this function is not square integrable in that just by the Kolmogorov two-series theorem, in that the variance of this term is 1 over n. So it gives the harmonic series. Square integrable, I mean in here under just the usual Lebesgue measure on the unit circle. So this function is almost surely not square integrable. But the zero set does not determine the function uniquely. So a question arises whether there could exist a square integrable holomorphic function with this zero set. So is this a zero set of a square integrable holomorphic function? This is a rather subtle analytical question. So whether a given subset of the unit disk is or is not the zero set of square integrable analytic function. But the usual criteria, there is a number of criteria in the literature, they all have the form, roughly speaking, that, well, in fact, if there are few zeros So the fewer the zeros, the easier it is. If there are few zeros, then you have such square-integrable holomorphic function. If there are too many zeros, then it is not possible to have such square-integrable holomorphic function. But this random set falls precisely in the critical situation. So all the explicit criteria, they do not, this is exactly the critical situation, they do not give a possibility to answer this question. And so, but in fact, it is true, so just it is joint work with Alexander Shamov of the Weizmann Institute and Yanqi Qiu, of the Chinese Academy, that just this set, in fact, let me formulate it in the following way, this set, the set X is almost surely a uniqueness set for the Bergman space. Uniqueness set for the Bergman space. So here, let us again recall that the Bergman space, I denoted A square of T, is the space of holomorphic functions of the disk, and in L2 of the disk with respect to the usual linear measure. So this is the Bergman space. So, yes, so this set is in fact almost surely a uniqueness set for the Bergman space. And again, I will explain a little bit later how precisely the action of the isometries plays a role in this. In fact, this action of the isometries is mixing. It is mixing. It has the Kolmogorov property, and just this is behind the argument. Okay. Yes.
Could you explain what uniqueness set is?
Can you please say again?
Could you explain what uniqueness?
Excuse me. Yes. Excuse me. I didn't. I said this, but I didn't write. Yes. So again, uniqueness set means. Thank you very much. Excuse me. Uniqueness set means that if F is in the Bergman space and F in restriction to X is equal to 0, then in fact F equals 0. Or in other words, yes, equivalently a Bergman function is uniquely determined, that's why uniqueness set. Equivalently, a Bergman function is uniquely determined by its restriction, which is why unique. Determined by F in restriction to A. Okay, so there we go. Okay, so the very definition of uniqueness set. By the way, let me also say very briefly that there exist different stronger versions of uniqueness. For example, that the Bergman norm, the square-integrable norm of the function f, is comparable to the norm of the restriction considered in small L2, so the sum of squares of the values. So none of this holds. This is not true. None of this holds, and precisely for the reason of mixing, because ergodicity and mixing, because in fact, well, it is not very difficult to imagine that there will exist very small balls, Lobachevskian balls, just with very many points, with positive probability, and precisely ergodicity ensures that such small balls will be found infinitely often, but that precisely contradicts a possibility that the norm of the function be comparable to the norm of this restriction, because the norm of this restriction will sometimes explode. Will sometimes explode when you're in such small ball. In such small ball, I'm saying with very, very many particles. So then the norm of the restriction will be very large, but the norm of the function, no. So, okay. So now the question arises, since it is a uniqueness set, how do I recover my function from this uniqueness set? So the function can be in principle recovered. It is uniquely determined by its restriction. How is it possible to do so? So the subtlety of this problem lies in the fact that the finite part of the set does not play a role. The finite part of the set does not play a role. What do I mean by this? Well, in fact, if the set X is a uniqueness set and I remove one point from it, it is still a uniqueness set. So holomorphic functions on the disk, if you multiply it by Z, it is still holomorphic function. So if there is a uniqueness set, then removing a point from it still makes the uniqueness set, and removing, in fact, 2 points from it still makes it a uniqueness set, and removing, in fact, the points which are the zero set of Lobachevsky product still keeps the fact that it's a uniqueness set. So, in fact, it's only the asymptotic properties of this set that should play a role. Only its behavior on the absolute of the Lobachevsky plane that should play a role. And in fact, this remark leads us to the idea, indeed, of using the Patterson-Sullivan construction in this problem. So, just maybe let me write here. So I consider the following sum, just that one Peres series. So I consider the exponential of S will be the parameter of the distance. D will stand for Lobachevskian distance. D is the and I just write the distance from given Z to X. X will be the particles of my configuration. So these are the X. So I take the limit as S goes to 1. And I claim that this is f of z. So several points are in order. So the sum in the numerator does not converge absolutely. It does not. In fact, so Bergman functions, so let me say one thing. So functions that are very familiar are Hardy functions. So Hardy functions, they have boundary values. Then, of course, if my function has boundary values, then there is no problem to recover it because my infinite set accumulates at the boundary, so I recover the boundary values and I recover the function. End of story. But Bergman functions very much do not have boundary values. Bergman functions can and do behave very wildly at the boundary. The only sense in which boundary values can be defined is in some sense of negative Sobolev regularity -1/2, I believe, and but this is completely useless. This is useless. The fact that its boundary values are a Sobolev distribution of regularity -1/2 is completely useless. At least, well, if it is not useless, then I don't know how to use it. So in this situation, I have some finite points. So what do I do? This sum, so this sum has to be understood in principal values. So in principal values over annuli. So over annuli, the sum makes sense. Okay, so and this is result in joint work with Yanqi Qiu. So just let me say that the quantifiers in this result are tricky. What do I mean by this? So this statement holds almost surely. So how does it hold almost surely? It holds almost surely in the following sense. For any f in the Bergman space, and almost every x, well, and in fact all z, but this is the least of our worries, and all z in the Lobachevsky plane. So this holds. This holds. So this is the statement. This is nice, but not quite nice enough. So the implied set of zero measure, which I throw away, the implied set of family of subsets of zero measure that I throw away, is indeed dependent on f. So this statement says that almost every set returns to me every f. Almost every set returns to me all f. But this interpolation result is weaker. It is weaker. It only says that for fixed f, almost all sets are good enough. And so, of course, the natural question arises whether the quantifiers can be written in the opposite order. And in fact, they can't. And we prove that they can't. So we prove that no such linear interpolation is possible for all f, So just if you write, if we write instead of this weight, any weight we like, it will not recover all functions f. And the reason for that is extremely naive, that the variance of this statistic has a lower bound. The variance of this statistic has lower bound. I should make a technical remark that in fact we only proved it for radial weights. So here the weight only depends on the distance, just as in the classical Patterson-Sullivan construction, the classical Poincare series, the weight only depends on my distance from the point where I'm sampling the function to the point x, like here. So this is the case we considered, but we don't expect that non-radial weights would change the picture. So just the variance of this statistic is bounded below, and therefore it is not possible to recover. All functions by this procedure. So, and intuitively the reason is, of course, that if I have my x, so then this x somehow goes to the boundary, but somewhere at the boundary it accumulates a bit more. But, well, precisely if I send my function to be very wild precisely there, then that's the function I would not be able to interpolate. This is the, how do you say, the intuitive explanation. So the question arises, is it possible to have such uniform interpolation, maybe in some smaller subspaces of the Bergman space? And the answer to that is yes. So let me be very brief here and refer to the paper. Just the subspace, so the subspaces we consider are given by reproducing kernels, K, Z, W. So we consider reproducing kernels of this type. So let us recall that the reproducing kernel for the Bergman space, I will use it in a moment, is just the 1 over pi 1 minus z w square, and it is reproducing kernel in the sense that the projection operator on the Bergman space is given by integration along this reproducing kernel. And just, yes, so this is projection on Bergman space. Projection on, yes. So this is the kernel. So here one can see that for the Bergman kernel, these coefficients grow as the square of the index. Excuse me, I misspoke. The square is there. They grow as the first power of the index. They grow as the first power of the index. For the Hardy space, an is identical equal to 1. An is identical equal to 1. So we can go a little bit beyond Hardy spaces. We can consider the case where an grow logarithmically. If an is on the order of logarithm of n, then interpolation is possible. Interpolation is possible. So I should say that such spaces already fail to admit boundary values. So we go beyond technically the so-called Nevanlin class. Just still randomness helps me in the sense that functions do not admit boundary values, but I can recover them. Okay, so this much for the Patterson-Sullivan construction, and let me just emphasize that the question of finding a uniform construction in Bergman space, it remains open. It remains open. On the other hand, the Patterson-Sullivan construction, it also can be applied in several complex dimensions for complex hyperbolic spaces. Essentially, it goes over, it is extended without change. So this is the result. And now let me say that, of course, the key point, the key element in the argument, is that this zero set admits a very beautiful description, just due to Peres-Virag, a famous paper from 2003, in that this set is in fact a so-called determinantal point process. Determinantal point process. So determinantal point process, what do I mean by this? I mean by this that the infinitesimal probabilities of finding a particle in infinitesimal neighborhood of given points is given precisely by determinant and in fact of the Bergman kernel. So this is an amazing theorem of Peres-Virag, and just one of the reasons why it is so amazing is that still to this day, 20 years have elapsed, it's 2003, still to this day, a conceptual understanding of this theorem is lacking. There exist several proofs, different proofs, but so in fact, as they write, when they had this theorem, they saw that we will now prove a much more general theorem, just that all zero sets of Gaussian series, they are determinantal. They have this determinant structure. The advantage of the determinantal structure is that very explicit computations are possible. So, for instance, variances of such statistics and so on can be computed reasonably explicitly. So, but in fact, it's not true. So it is possible to tame this Gaussian series a little bit and obtain a series for which the radius of convergence is infinity. But that one is not determinantal anymore. It is possible to consider instead of Gaussian series, instead of Gaussian power series, a Gaussian Laurent series. So then it would live on the annulus, and it is a very beautiful problem, and it has been treated by Shirai and Katori quite recently, but just still it is not determinantal. In fact, in Gaussian, in work with Gaussian functions, the natural object that arises is the permanent, not the determinant. The permanent is the one that arises. So, and in fact, what arises there, more or less generally, is a product of the permanent with the determinant. But the determinant is much nicer than the permanent. And so it is just the fact that here somehow the permanent disappears and the determinant is the one who wins. It is completely, so as I say, there is no conceptual understanding why this happens. And there is no example and there is no proof. For example, here's a question. Let us consider such series with independent entries, but not necessarily Gaussian. Under what assumptions does it admit such determinantal formulas? Open question. I have no idea. So this is, let's say, this is the only example of which the context remains as little understood as the day after the theorem was proved. Okay, but for us, at the same time, it is clear, well, so I fulfill my promise that just it is clear that this Bergman kernel is Lobachevskian invariant, and so the zero set is Lobachevskian invariant. It is immediately clear from the Peres-Virag theorem, though it is not clear from the definition because, again, the Gaussian function itself is not, the distribution of the Gaussian function itself is not Lobachevskian invariant. And so this determinantal structure plays a key role in all the arguments. So in fact, the proof of this theorem with Shamat and Qiu in fact proves such uniqueness result for any determinantal process. So just this determinantal formula can be written for any projection operator, any kernel of any projection operator. It's possible to consider such determinantal formula, and it's possible to consider such point process, and this theorem holds for it. This theorem holds for it in full generality, but just and the key point in the proof of this, and especially of this, is precisely this action of isometries of Lobachevskian isometries. This action of Lobachevskian isometries on my infinite dimensional space, action which is again has strongly chaotic properties. Okay, so if there are any questions, please ask them, because now I want to turn the page and consider a completely different example. Yes?
Can you just repeat what is this determinant?
What is rho, you mean?
Yeah, what is
rho? Excuse me, yes, I was not very long on this. So again, I consider just my points Z1, ZL, and I consider an infinitesimal neighborhood around each of them, and this quantity rho L is the probability that in each infinitesimal neighborhood a particle be found.
So, but where is epsilon in this?
Epsilon is around Z.
No, but in the formula.
Excuse me, I already divided by epsilon to the L.
I see.
Yeah, excuse me, yes. I divided both sides by epsilon to the power L. So it has to be emphasized that these quantities are independent parameters of my infinite dimensional probability distribution of this point process. They're, roughly speaking, they're like moments of different order. So it is maybe intuitively one might think that the 15th correlation function determines the 14th, but in fact it's not true. So they're roughly like moments, but in fact here the moment problem is very nice. So there is no problem. The moments determine everything you need. If any further questions on this part, because now, as I say, I want to go to a completely different example. Okay, so we take leave of the Lobachevsky plane, but in fact only briefly. Yes, so there is, I have to erase, but this requires competence which I doubt. So, this is really nice. Yes. So the next example I would like to consider is maybe the most famous example of the determinantal point process is the so-called sine process. Sine process. So let us start with just the unitary group U of n. So, and to each matrix in U of n, I assign its spectrum, e to the I. So the spectrum of the unitary matrix, the eigenvalues belong to the unit circle. And so I can consider the push forward of the Haar measure under this map, and this push forward is given by the explicit formula. This is essentially the wild character formula. So, and it is, in fact, it can also be given determinantal form, and this, I think, is a remark which is due to Segur. So, that this is, in fact, a determinant of Kn e to the I theta k theta L, well, the same product. Where Kn is just the Dirichlet kernel. Okay. So, I would like to go to infinity in this construction. I would like to take now the dimension of my unitary matrix to infinity. It seems fairly clear already by looking at the determinantal formula below that the natural scaling is the following. So in fact, I can also explain it in the following way. A unitary matrix of format n has n eigenvalues. So these eigenvalues live on the unit circle, so there are n of them. Very many, they're very dense there. So I expand the unit circle by a factor of n in such a way that the distance between them be 1 rather than n. Okay, so then these measures converge to a probability distribution on the space of configurations, so as n goes to infinity. On the space of configurations on R, now I consider the space of configurations on R. So these are subsets or infinite subsets of R without accumulation points. And so the measure will be, just looking at this formula, the measure given by its correlation functions, which are, again, determinants, well, of the limit of the Dirichlet kernels. And this limit is, in fact, the famous sine kernel of Dyson. S x y is sine pi x minus y over pi x minus y. This is a very beautiful kernel. It is the kernel of projection. Again, it's a kernel of projection on very nice space. S, so the operator for which I keep the same symbol, is the kernel of projection on the Peres-Wiener space. Is the space of F in L2R such that the Fourier transform is supported in minus pi pi. So this is just projection on this Peres-Wiener space, and this is the sine process, maybe the most famous, historically the first and the most famous process of random matrix theory. So for the sine process, the uniqueness property, which I mentioned, with which I started the talk, it was proved before us. It was proved by Gauss. Who in fact built on previous work of Lyons. Actually, we also built on previous work of Russell Lyons, but in a completely different way from Gauss. So Gauss proved for the sine process, he proved that almost surely X is a uniqueness set. Almost surely X is a uniqueness set for the sine process. Again, we proved with Qiu and Shamov that it is true for any determinant process, but the proof of Gauss was specific to the sine process. Uniqueness set for the Peres-Wiener space. For the Peres-Wiener space. In the sense that, again, just as before, so I have my configuration on R. It's a random subset of R. Without accumulation points, but with accumulation clusters, I have to emphasize. So again, it's the same thing, but here it's the group R that acts. So the group R acts ergodically and with mixing and effect again with the Kolmogorov property. And so there exist some very small intervals which contain very many points. These intervals are extremely improbable. These intervals are extremely these intervals with very many points are extremely improbable. So they, please allow me to pursue a short digression. So the eigenvalues, they don't like each other. They repel each other. So it is very improbable that a random matrix have close eigenvalues. It is much less probable than if I would be throwing points at random on the unit circle. So there would be much more clustering if I throw points at random, and much less if I consider eigenvalues of a random matrix. But in the case of the sine process, it is even more improbable. So the probability will decay as factorial. So the square of the number of particles, is sub-Poissonian. Not just the number, the square of the number of particles is sub-Poissonian. So the probabilities decay very fast indeed, but yet it exists such small intervals with very many particles do in fact exist. So sometimes there are, for almost every configuration, somewhere they realize themselves. So it is a uniqueness set, but again, the problem of interpolation from this uniqueness set is completely different. So let us, for the Peres-Wiener space, the first result on interpolation is the famous theorem of Kotelnikov from 1970. So that just if I have a function in Peres-Wiener space, then of course f of x is equal to sum just f of k sine phi x over phi x minus k. So a Peres-Wiener function is recovered from its integer values. Knowing the integer values of a Peres-Wiener function recovers the Peres-Wiener function. This is the theorem of Kotelnikov, and just the point of the Kotelnikov theorem is that, as opposed to the previous situation, as opposed to the zeros of the Gaussian analytic function, where neither of the zeros counted individually. So, in fact, it is clear also from this formula, if I throw away one zero, this formula doesn't change. So, the opposite takes place in the Kotelnikov theorem. Every point in Z counts because, in fact, so the Kotelnikov theorem, it is completely precise. Here is a function, here it is, which is Peres-Wiener and is zero at all points except k. So it's written quite explicitly. It's just the shift. It's just the shift of the cardinal sign function. Well, because in fact, the Peres-Wiener space is invariant under shifts. This is clear from its definition. So not only the point, and this is in complete opposition to the previous case, not only is the set Z a uniqueness set for the Peres-Virag space, but it is also a minimal uniqueness set. If I remove one point from it, it is no longer a uniqueness set. There will be a function which is 0 everywhere except this one point. Please allow me to emphasize that, in fact, as our very first example shows, the uniqueness set need not admit a minimal subset. So somehow all this terminology is dictated by analogies with linear algebra, but in fact these analogies fail. So there can be a complete subset but which does not have a uniqueness subset. In fact, just precisely the example we just considered. If I remove one point, it's still a uniqueness subset. So this situation is different. Here there is a excuse me. Here there is a complete set. So the set Z, it recovers every Peres-Virag function, and it is a minimal set in that no proper subset of it satisfies this property. So already these considerations motivate the question regarding the theorem of Gauss. So is this set in fact a uniqueness set? Is this set in fact a uniqueness set? So the answer is no, but almost. So no, but almost. In fact, it will be a uniqueness set if I remove just one particle. So this is just maybe the main result of this talk, is that just the sine process has axis 1. That is to say, almost every trajectory is not a uniqueness set. But if I remove one particle, then it is. Excuse me, it's not, please excuse me, I misspoke. It's not a minimal set. Please excuse me. So it is, of course, a uniqueness set. It is not a minimal uniqueness set. It is not, so X is not minimal. But X without one particle is. But X without one particle is. So it is a yes.
Just Z over X. So this looks even more. Product is understood in principal value, by the way, just taking the product over symmetric intervals. So, and then it converges. So this looks even more like the Euler product for the sine function. So, and now I just pick out 2 points. So I consider I divide by x minus q. So I kick out 2 multiples. Excuse me, z minus p, excuse me, z minus p, z minus q. Z minus p.
So, roughly speaking, it's the following. So the sine function is not square-integrable. But if I kick out one multiple in the Euler product, then it is. So it's the same thing, except I have to erase 2 of them. So this one is in Peres-Virag space. This one is in Peres-Virag space, and this is the easier part of the theorem. The part that costs more effort is the proof that if I erase only one, then it is not. So in fact, by various more or less abstract arguments, which are also applied beyond the sine process, what I need to prove that this function g, I'm a little bit inconsistent. Please excuse me. G, okay. Gx,
gx of z over z minus p is not in L2 of R. Is not in L2 of R. I write this function of a complex variables because in fact I will need it as a function of a complex variable, but of course when I speak about Pelley-Wiener space and so on, I mean in restriction to R. So yes. So also, by the way, now already from these considerations, it is clear that which particles P and Q, it doesn't matter, because this statement, if it's true for one pair of P and Q, it's also true for any other, because it will, such change will not affect square integrability, and similarly here. So already this part is clear, that which particle doesn't matter. So now the question is why this? Why does this hold? So, and let me first explain informally, and then I will explain formally. So, informally, the reason is the following. So, in the Euler product for the sine function, all the contributions of the different multiples, they cancel out very nicely, and so the sine function is bounded. If I move these particles even very little, at some points the product will explode. At some situations the product will become very large. So in fact the product will, it is an effect of the form of central limit theorem. So at some points there will be big explosion of this product. And so this is the imprecise explanation. So randomness makes this product bigger in some parts of the line, but this is already enough to ensure non-square integrability. So this is informal explanation, and now let me give formal explanation. So in fact, formal statement is that this function considered as a measure converges to a random measure, and in fact to a very famous random measure, to so-called Gaussian multiplicative chaos. But this maybe I will be a little bit vague. But let me just say that the function. Let me just say the following: that just this function, in fact, I consider the following scaling: I plus RT and W just goes to infinity RI. So this scaling, this function, to some power gamma, and over the expectation of this. So normalized to have expectation 1. And considered, so gamma is from 0 to 2, between 0 and 2, but in fact this is good enough for ensuring this. So I don't consider the actual square, it's, the situation is more subtle, square is, the number 2 is critical, but this is enough for my purposes. This is enough for proving this. So this is now a measure, this is a measure, 0. So just from this follows this. And so now let me say very briefly in the 5 minutes I believe I have, is this right?
A little bit longer, we started.
Okay. So let me just say very briefly, and maybe right here. So yes, so this will be okay. This will be enough. So just where this random measure comes from. So it is already clear that this quantity is very similar to characteristic polynomial of a matrix. In fact, characteristic polynomial of a matrix, it's not possible to consider a limit of characteristic polynomial. Matrix becomes bigger and bigger and bigger, and so characteristic polynomial, there is no limit. But it is possible to consider the ratio of two characteristic polynomials. The ratio, this is just the ratio, so remember that x arose as eigenvalues of a unitary matrix. So this is just, so there is some limit procedure, so this is just the ratio of values of characteristic polynomials, and this clearly admits limit transition. So here it is. So I'm interested in the behavior of these ratios of values of characteristic polynomials, and this, by the way, was studied by Fedorov and Keating. So and there were many other researchers I will mention. So just the, let me consider instead of this characteristic polynomial, let me consider its logarithm. So instead of this product, I consider the sum. So I consider additive functional. So the sum of the values of some function, like this, over the trajectory of the sine process. And then this additive function satisfies very beautiful central limit theorem of Soshnikov, and also Soshnikov was building on the work of Kurt Johansson. So just the S, when the function f is expanded by r, and this is the same r as here. When f is expanded by r, this S, in fact, converges to the normal distribution. And the variance of this distribution, this is very important, is the Sobolev 1/2 norm. Sobolev 1/2 norm of the function f. Let me not, let me write very quickly the definition of the Sobolev 1/2 norm. It's not the norm, it's rather the semi-norm, which is why I put this dot. It is just the following integral. And the key point here is that this integral is invariant under scaling. By the very definition, it's invariant under scaling, under homotheties of the line. Well, in fact, if function under homotheties converges to something, then the limit might better be invariant under scaling, and well, the Sobolev seminorm is the only one that is invariant under scaling. But it is not just invariant under scaling, the Sobolev seminorm, it is also invariant under Lobachevskian isometries. So the Sobolev seminorm, it is useful to consider the line as the absolute of the Lobachevsky plane. And in fact, when I consider this sum of this product, and I consider this sum of logarithms, so I consider sum of logarithms, so sum logarithm z minus x minus w minus x. I take z and w to be on the upper half plane. And then I take the Soshnikov central limit. Then the resulting Gaussian for this function, it can be computed quite explicitly. And so I obtain a Gaussian random process indexed by pairs of points on the Lobachevsky plane. So here it is, for the moment I consider it on the upper half plane, but in fact it doesn't matter. So and the variance is the following. It is the logarithm of 1 plus cosine hyperbolic of the distance. Cosine hyperbolic of the distance. And of course there is also, well, clearly from this, there is also the cocycle identity YQ plus YQR plus YRQ equals 0. The cocycle identity. This defines a Gaussian process uniquely. So I have this Gaussian process, it is indexed by pairs of points on the Lobachevsky plane. This is the covariance. It is just explicit computation of this Sobolev 1/2 norm for this function. And well, and there is cocycle identity, which is also clear. Okay. But now, we all know very well that in Lobachevsky plane, so this quantity is roughly speaking distance. Roughly speaking distance. It's distance plus something. So let me consider this Gaussian process. I fix P, I will call it now O, and I consider it on a circle on the Lobachevsky plane. Very good. Gaussian random variable, so on each point, now that I fixed one of the P's and Q's, or to each point corresponds a Gaussian random variable. The variance of the Gaussian random variable is roughly the distance. So as the circle grows, the distance becomes bigger and bigger.
But the covariance, the variance goes to infinity, but the covariance, as is immediate from the formula, is the Gromov product. So the covariance, when points go to the absolute, the covariance, in fact, the Gromov product is just the distance to the point of tangency of the inscribed circle. So the Gromov product goes to a finite limit. So the covariance, so on the absolute of the Lobachevsky plane, I have not Gaussian process, it is not possible, because the variance goes to infinity. But I do have limit covariance function, just the Gromov product is extended without any difficulty. Limit covariance function, so I have Gaussian field, so Gaussian process in generalized sense. So Gaussian, not Gaussian random variables, but generalized random variables. Generalized Gaussian random variables, because again, the covariance being the Gromov product is roughly the Gromov product. Roughly the Gromov product. So just, yes, so it extends to the boundary. But in fact, it is already, in Gaussian case, it is already classical theorem of Jean-Pierre Cahan that if I have Gaussian field, so on each circle I have honest Gaussian process. On the absolute I have Gaussian field. But this Gaussian field, here it is, it has well-defined correlation function. But Jean-Pierre Cahan teaches us that for such Gaussian field, it is possible to define the exponential, the normalized exponential. There exist, by the way, several, so with some parameter gamma, where parameter gamma has to be sufficiently small. It is possible to define, well, it is of course possible to take such exponential before passing to the absolute, there is no problem in that. But in fact, it is also possible to take this exponential on the absolute. It will no longer be an absolutely continuous measure. In fact, it will almost surely be a singular measure. But it still will be a non-trivial random measure. And the reason for this, again, is just that the Gromov product is continuously extended to the boundary. And so this family of measures converges to the Gaussian multiplicative chaos. This is a theorem that goes back to Jean-Pierre Cahan, but in fact there exists several approaches to this result. So one of Shamov also. The most convenient for me in this is the approach of Nathaniel Berestitsky, which is based on Gersanov theorem. So it is very convenient in this situation to use some type of Gersanov theorem. But just I wanted to say that, of course, proving that this converges to random measure is not the same because these ones are not Gaussians but only symptotical Gaussians, and this is where one needs to do some proving. But my point, however, is that the fact that there is this action of Lobachevskian isometries on the logarithm of the characteristic polynomial of random matrix allows one to pass to a random measure on the absolute, and then allows one to prove this. And I think it would be very interesting to understand conceptually why Lobachevskian isometries arise in such a way in the study of random matrices. Thank you very much.